Green hydrogen is the term used to describe the hydrogen produced by using electricity from the renewable sources, such as solar and wind, for water electrolysis. The green hydrogen can be stored and used for various purposes such as for producing electricity, running fuel cell-powered cars, for industrial applications and also for producing dimethyl ether using power-to-X technologies that are being developed under the banner of European E2C project. Producing hydrogen using intermittent sources have its own challenges. The power is not available all the time and the intermittent nature of the sources may lead to lower efficiencies and accelerated degradation of the components. The whole system is highly complex due to the presence of multiphysics phenomena. Also, due to the involvement of hydrogen gas, the safety of the system as well as the operator is of prime importance. There is a requirement of the solution to make these kind of system more efficient and safer to use. Mathematical modeling could be the answer to these challenges. Mathematical model is a set of differential equations that allows us to see the evolution of outputs based on the inputs and process parameters. Mathematical model of such complex system can be used for studying the real behavior of components, subsystems and overall system behavior under dynamic intermittent operations in various operating conditions. A good model can not only be used for process simulations but also helps to develop control and diagnosis algorithms to run the system smoothly, safely and efficiently. The model can also be used for systems health management. Here at University of Lille, a generic dynamical multiphysics model of PEM electrolyser running on intermittent sources has been developed using bond graph approach. The developed model has various key features. The developed model consists of submodels, known as capsules, that can be easily modified to fit any configuration of PEM electrolyser. Because of the generic nature, it can be easily sized and scaled as per the requirement. The model incorporates the calculation of efficiency at subcomponents level to estimate the performance of the electrolyser. Also, the system dynamics and the different thermal losses can be predicted which cannot be done in the real process. The model can also be used for the development of control algorithms and diagnosis algorithms for online implementation. For online fault detection, the estimated outputs of the model are compared with the actual values from the real process measured using sensors. The difference between the two is known as residual and its value is 0 in the absence of the uncertainties. The non-zero value of the residual indicates the occurrence of fault in the system. However, in actual practice, the value of residual is usually non-zero due to the presence of uncertainties such as parameter uncertainties and measurement uncertainties. Therefore, in order to avoid false detection, upper and lower bounds for the residuals are used known as thresholds. In normal operating conditions, the residual do not cross the thresholds. When a fault occurs in the system, the respective residual value crosses the threshold limit and the alarm is generated. Not all residuals are sensitive to the fault occurred. Therefore, by knowing which residuals have crossed the thresholds, the fault can be isolated. Various subsystem level efficiency can be calculated in real time using developed model. As the model is based on the power exchange between different elements, one only needs to know the input power. The power at the input and output of every subsystem is known. The efficiency is calculated as the ratio of the output power to the input power, where output power is the difference between input power and the estimated power loss. With the help of real-time efficiency calculation, the system inputs and parameters can be adjusted in order to improve the performance of the system. The hybrid multi-source hydrogen generation platform, available at Polytech Lille, has been used to demonstrate the effectiveness of the developed model in online efficiency calculation and diagnosis for fault detection and isolation. The platform consists of photovoltaic panels, wind turbine, and batteries interconnected to the common DC bus presented by the electrical cabinet. This electrical cabinet contains the power converters which are used to control the power flow, and the controller used for supervision. The electrolyzer uses the power produced by photovoltaic panel and wind turbine to produce hydrogen gas, which is stored in the metal hydride canisters. The produced hydrogen can be used for several applications, such as for producing DME using the said MES process or supplying the fuel cell to generate electricity. For the implementation of the developed algorithms, data acquisition is required, which is performed using a controller and a Windows-based computer system. There is local communication between the two, which is realized to get the data of the sensor measurements and generate the control signals to act on the actuator to control the power flow between the HMS components. A GUI has been developed using MATLAB Simulink in order to exploit the developed model for real-time efficiency calculation and for supervision of the platform by generating the fault indicators for fault detection and isolation. This is the graphical user interface developed in MATLAB Simulink. This GUI incorporates all HMS components model used for online diagnosis. These blocks represent the efficiency calculation deduced from the developed models of each component. Here is the GUI in operation in real time for platform supervision. Using this GUI, one can monitor the measurements of different sensors. One can also monitor the fault indicators in order to detect the occurrence of fault and monitor the efficiency of different components in real time. The effect of the intermittency of sources on the efficiency of the electrolyzer can be seen. The intermittency of the sources does not allow a constant production of hydrogen. For the validation of the effectiveness of the diagnosis algorithms, the faults are injected into the platform and the evolution of the fault indicators with their adaptive thresholds are verified. 3 faults have been considered for the demonstration. 2 component faults are introduced by affecting the internal resistances of the battery and the photovoltaic panel. Valve blockage fault is introduced by shutting off the hydrogen flow valve at the output of the electrolyzer. This demonstration corresponds to component fault in the photovoltaic panel. To introduce this fault, we have to vary the resistance to push the internal resistance above the acceptable limits. On the right side, we can see before the injection of the fault, the residuals are within thresholds. When the fault is injected, the residuals 1 and 2 goes out of the thresholds. This shows only these residuals are sensitive to this fault. The fault is injected in the battery in the similar way as it is done for the photovoltaic panel. On the right side, we notice that only the residuals 2 and 3 are sensitive to this fault as they went out of the thresholds when the fault has occurred. The blockage fault is injected in the electrolyzer by closing the valve of the cylinder during the operation of the platform. In this case, only the indicators 2 and 4 are sensitive to this fault as they went outside the thresholds when the fault has occurred. According to these demonstrations, it can be seen that each residual is not sensitive to all the faults. For example, the fault on the panel influence only residual 1 and 2. The fault on the battery influence only residual 2 and 3. The blockage fault in the valve influence residual 2 and 4. According to this analysis of the fault signature matrix, we can conclude that the faults can be isolated when they occur. From these demonstrations, we can conclude that the modeling is very important for engineering tasks. The developed model can be effectively utilized for fault detection and isolation. This allows us to select cost-effective maintenance strategy, and we can reconfigure the system easily in order to implement robust control. Also, the model is effective in carrying out online calculation of efficiency, which allows us to estimate the dissipated power and take appropriate decision for maximizing the performance of the system. These strategies will ensure the availability of the energy. What we can offer. We can provide the dynamic model for the development of optimal operation mode management algorithms, and to carry out the study to check systems reliability. We can help for the implementation of online diagnosis and health management algorithms, to ensure the safe and efficient operation of the hybrid multi-source platform for green hydrogen production. We can help reducing the maintenance cost by selecting the best possible maintenance strategy for multi-source platform equipment, such as wind turbines, solar panels, electrolyzer and fuel cells. We can offer feasibility testing and technical and economic calculation before the installation of green electricity production and storage facilities. With our expertise and set of skills, we can help in decreasing the production costs of decarbonated electricity. We can help in realizing the online monitoring of energy efficiency. Thank you for your attention.